This is Group E's Module 5, Lesson T115, Materials and Manufacturing of Precast Prestressed Concrete module. We will cover three topics. We will cover materials, manufacturing, and handling, transportation, and installation. Materials include concrete, grout, pre-stressing steel, post-tensioning, mild or non-pre-stressed reinforcement, and fiber reinforced polymers. Concrete composition relies on one of three cement categories: ASHTO M85, M240, or ASTM C1157. The ASHTO M85 offers various types, including Type 1 for normal use, Type 2 for moderate sulfate resistance, and Type 3 for high early strength, Type 4 for low heat hydration, and Type 5 for high sulfate resistance. Each type can have air and trained versions, with Type 2 being the most, with being unique for its potential for moderate heat and hydration, or moderate heat of hydration and sulfate resistance. ASHTO LRFD bridge construction typically utilizes types 1 through 3, with type 3 often being preferred for its characteristics. The ASHTO M240 categorizes blended hydraulic cements featuring type IS for Portland blast furnace slag and type IP for Portland pozzolan cement. Each type can possess specific properties, such as air entrainment, sulfate resistance, and heat of hydration variations. Lastly, hydraulic cement types under ASTM C1157 include GU for general use, HE for high early strength, MS for moderate sulfate resistance, and HS for high sulfate resistance, MH for moderate heat of hydration, and LH for low heat of hydration, catering to diverse construction needs. Concrete includes aggregates, which are crucial for its properties. For normal weight concrete, fine aggregates should adhere to the ASHTO M6 standard, while coarse aggregates should meet ASHTO M80 specifications. In the case of reduced density, lightweight concrete, aggregates should conform to ASHTO M195 standards. Factors such as size, gradation, shape, and texture of aggregates influence the water content and workability of the mix. Determining the maximum aggregate size depends on various factors such as mix design, rebar spacing, cover thickness, and member thickness. Additionally, precautions should be taken if any aggregates are prone to alkali aggregate reactivity to prevent potential issues. Concrete requires potable water or water meeting ASHTO T26 standards, ensuring cleanliness and freedom from harmful substances like oil, salt, acid, alkali, sugar, and vegetable matter. According to ASHTO LRFD construction specifications, chloride ion concentration should be below 1000 ppm, and sulfates should be less than 1300 ppm to prevent adverse effects on concrete performance. Supplementary cementatious materials like fly ash, ground granulated blast furnace slag, and silicon fume can be used in concrete to partially replace cement and enhance various properties. These materials react chemically with calcium hydroxide to contribute to the cementatious matrix of concrete. Fly ash, a residue from coal combustion, comes in two classes, F and C, each with distinct properties affecting workability and initial setting time. Ground granulated blast furnace slag, known as slag cement, offers benefits such as increased strength, reduced permeability, and improved resistance to various forms of deterioration. Silica fume, a byproduct of electric arc furnaces, enhances early age strength and decreases permeability, but it can increase water demand. Care should be taken to ensure the availability and compatibility of these materials before specifying them in concrete mixes. Chemical admixtures play a crucial role in concrete formation, offering various functionalities to enhance its performance. These include water reducers, superplasticizers, retarders, accelerators, cor- uh, corrosion inhibitors, trainers, and shrinkage reducers. When using multiple admixtures, it's essential to ensure compatibility with each other and with the cement. Consulting the manufacturer for guidance and possibly conducting trial batches. Water reducers decrease the water to cement ratio by 5 to 10%, improving workability while maintaining or enhancing strength. However, this can pose challenges in finishing due to reduced bleed water on the surface. Superplasticizers, on the other hand, decrease water content by 12 to 30%, providing high slump and increased flowability um, with a brief period of heightened workability followed by rapid loss. Retarders slow the setting time, which is beneficial for intricate placements or special finishes, and counteract the effects of hot weather. Accelerators expedite finishing operations, which is particularly useful in precast settings and cold weather conditions. Accelerating concrete setting and high early strength development while reducing curing time. Corrosion inhibitors are vital for slowing the corrosion of reinforcing steel and concrete, particularly in structures exposed to high chloride concentrations like marine facilities, bridges, and parking garages. While beneficial for corrosion protection, some inhibitors may also impact concrete setting, air content, and shrinkage cracking. Air trainers uh, introduce stable microscopic air bubbles into concrete mix into the concrete mix, reducing its strength but enhancing durability in freeze thaw environments. These air pockets accommodate water um, expansion during freezing, mitigating internal pressure and enhancing concrete's resistance to damage. Meanwhile, the shrinkage reducers decrease drying shrinkage by 25 to 50%, minimizing cracking and curling, particularly in flat cast products. While they have little effect on slump and air content, shrinkage reducers may slightly delay setting and high early strength development.
So now we're going to talk about the concrete like strength. So the concrete strength for precast pre-stressed members primarily hinges on the strength necessary at pre-stress transfer, especially if transfer occurs shortly after casting, sometimes within 18 hours. Typically, allowable stresses in the concrete during pre-stress transfer are set at 65% of the F prime C for compression, F prime CI for compression, and limited to 0.0948 square root F prime CI for tension in areas without bonded tendons or reinforcement, not to exceed 0.2 KSI. However, in regions with bonded tendons or reinforcement, the limit is 0.24 times the square root of F prime CI, with bonded reinforcement proportioned to resist total tension calculated assuming an uncracked section at a steel stress not exceeding 0.5 Fy and 30 KSI. The required concrete strength at shipping should be specified with some states mandating additional impact as dead load during shipping or various construction stages. Engineers may also need to specify concrete strength at the time of the member erection or post-tensioning, depending on the project's requirements, with F'(C) specified for service conditions as usual. Now we're going to talk about the high performance of concrete. High performance denotes concrete with a specific performance or uniformity criteria, distinct from high strength. Although high strength concrete exceeding 8 KSI may fall under the high performance category, other high performance variants include low permeability and self consolidating concrete, which doesn't necessitate mechanical consolidation like vibration during placement, streamlining the process. Additional high performance attributes encompasses during durability for harsh environments like coastal or dicing salt exposed areas, and workability to fill spaces without voids or segregation. Ultra high performance concrete, also known as UHPC, stands out for exceptional durability, high compressive and usable tensile strength, long-term stability, and flowability. A bed with unique materials requirements and steel fiber reinforcement, differentiating it from conventional concrete mixes. So now, density and strength. So the first crucial property of concrete is density, essential for calculating structure, weight, and material modulus of elasticity. Table 2.4.71.1 from the PCI Bridge Design Manual offers density values for plain concrete, with lightweight concrete assumed at 0.11 kips per foot cubed, though some products may achieve densities as low as 0.095 kips per foot cubed. Sand lightweight concrete typically stands at 0.12 kips per foot cubed, which normal weight concrete with F prime C less than 5 registers at 0.145 kips per foot cubed, with densities between 5 and 15 ksi, calculated using the formula 0.14 plus 0.0015 times F prime C. Controlled density mixtures achieved by blending lightweight and normal weight aggregates enable the manipulation of concrete density to meet specific requirements such as beam weights for shipping or lifting limitations. Moreover, due to the higher density of reinforcing and pre-stressing steel compared to concrete, they add about 0.005 to 0.01 kips per foot cubed to the plain concrete density, with potentially more significant increases for heavy reinforcement elements. Concrete compressive strength measures through testing of cylinders varies with time and can be estimated using the formula F prime C. T is equal to F prime C times 28 times T over the combination of A plus B times T, with values of the constants A and B available from ACI 209 or the PCI Bridge Design Manual. So now we're going to talk about these qualities. The modulus of elasticity, representing the stress-strain relationship in the linear elastic region of a material stress-strain curve, varies with time for concrete. For concrete strengths below 15 ksi, it can be calculated using the formula EC equals 120,000 K times K1 times WC time squared times F prime C to the 0.33 power, where K1 is a correction factor for aggregate source, generally taken as 1 unless specified by the jurisdictional authority. This calculation is applicable for unit weights ranging from 0.09 and 0.155 kips per foot cubed. The modulus of elasticity serves as a crucial role in various calculations such as camber, elastic deflections, axial shortening and elongation, pre-stressing losses, and composite section properties. Additionally, over time, concrete experiences creep and shrinkage, particularly relevant in pre-stressed concrete members, leading to significant losses in pre-stressing force. The extent of creep and shrinkage depends on factors like concrete aging at loading, stress level, relative humidity, and strength, and member size, and presence of non-pre-stress reinforcement. Concrete's coefficient of thermal expansion influencing its expansion or contraction due to temperature changes is vital to designing bearings, connections, and expansion joints, with variations based on aggregate size. detailed in the PCI Bridge Design Manual, Chapter 2. So the next material is grout. Grout serves multiple purposes in construction. Connecting precast members, supporting structural members with grout beds, and filling ducts for post-tensioning tendons. It's manufactured to minimize shrinkage during curing, ensuring it doesn't contract within filled voids. Epoxy resin grout enhances bonding or tensile capacity, and grout can also be dry packed into voids instead of being poured on or pumped as a fluid mixture. So now we're going to talk about the steel reinforcement. The materials used in pre-stressed concrete members includes pre-stressing steel, which is available in two main types: low relaxation and stress relieved strands. While stress relieved strands are no longer referred to in the ASTRO LRFD bridge design specifications, they do still remain in use for evaluating existing structures. Typically, low relaxation strands exhibit fewer losses compared to stress relieved strands. These strands come in various grades, with 270 KSI being the prevalent choice for bridge members, though 300 KSI grade is also available. Each strand comprises 7 wires, typically uncoated but can be epoxy coated, with precautions needed during installation and stressing to prevent damage to the epoxy coating. Additionally, strands can be smooth or indented to enhance bond and decrease transfer lengths. Pre-stressing steel is crucial for pre-tensioning and post-tensioning applications. With relaxation losses occurring over time, more significance in stress relieved strands. Furthermore, detailing considerations include strand placing, spacing, and diameter selection, with fewer larger strands often proving more cost effective despite being stiffer and more challenging to work with. Post-tensioning materials used in pre-stressed concrete include tensioned strands or bundled tendons, with special anchors embedded in the concrete to secure them. Ducts are placed before concrete passing to house strands or tendons with specifications for diameter and material. Additionally, post-tensioning bars with minimum ultimate tensile strength of 150 KSI are sometimes preferred, particularly for short tendon profiles or connections between precast members. Mild or non-pre-stressed member reinforcement is also essential for various applications, such as providing continuity in slabs or enhancing bending moment strength. Detailing considerations include constructability and interference with strand placement, with options ranging from lap splicing to weld wire reinforcement sheets are as alternatives to reinforcing bars. Ultimately, careful consideration of detailing choices ensure both structural integrity and cost effectiveness in pre-stressed concrete construction.
Okay, Now I'll talk about girder stability. Um, so there are five main phases over the life of a precast pre-stressed concrete girder, and those five phases are lifting, storage in the pre-stressing yard, transportation to the site, erection, and construction. Over all the phases, the lateral stability of the girder must be considered and checked. At any time where the girder is lifted, there may be no rotational restraint at the lifting hooks, meaning lateral instability is always possible. When stored, the girder is placed on a wooden dunnage with no rotational support. During transportation, the girder's stability may be affected by the truck stiffness, wind load, centrifugal force, or change in the wheel path. When erected, the girder must be properly braced to prevent rotation on the supports. Construction loads may also cause lateral instability of the girder. This is why during each stages of the girder, you have to consider lateral stability. So next we'll cover the criteria for girder stability. Um, the analysis of girder stability should conform to the accepted industry practice. Um, the recommended practice establishes criteria pertinent to the design of precast pre-stressed concrete girders, lifting devices, bearings, and bracings that may be required to provide an acceptable factor of safety for lateral stability. The four main criteria for girder stability must include defining the assumed design and construction loads, identifying assumed material properties, specifying tolerances for construction, and establishing stress limitations and overall factors of safety. Um, Continuing on to the girder stability design and construction loads. Um, Assumed design and construction loads typically consist of permanent loads, transient loads, and environmental loads. Some of the permanent loads that are considered are the dead load of the structural components and the pre-stressing force due to creep and shrinkage. Some of the transient loads that are considered are the dynamic loads, centrifugal force, and construction live load. The environmental loads that are considered are the wind loads, thermal effects, and seismic loads. So going a little bit more in depth on the dead loads of structural components, one of the big considerations is concrete unit weight. The normal weight of reinforced concrete is assumed to be 150 PSF, or PCF. Lightweight reinforced concrete unit weight varies from 100 to 140 PCF. Heavily reinforced dense concrete may be as high as 170 PCF. The weight of falsework and supports must also be considered. The ASHA Guide Design Specifications for Bridge Temporary Works from 2008 specifies a minimum of 160 PCF for normal weight concrete and 130 PCF for lightweight concrete. This includes the weight of the reinforcement and the falsework of the beam. Actual dead loads depend on the materials used in fabrication of the girder and construction of the bridge. The engineer should always have a knowledge of the materials used and adjust the calculations accordingly. The next category we'll discuss is the factor of safety. The factor of safety against cracking is defined as the resisting moment divided by the active moment that you can see in the equation down at the bottom. Um, this is also the factor of safety based on the equilibrium post-cracking. Um, Mast, who wrote one of the governing books about factor of safety and girder stability, recommends that the factor of safety should be greater than 1, that we can also see down here at the bottom. Next, we'll talk about the cracked section angle of rotation, also having to do with the factor of safety against failure. Um, so first of all, theta is varied to find the maximum factor of safety. Um, And by differentiating the equation for the factor of safety against failure with respect to theta, the maximum tilt angle can be computed. And the maximum tilt angle is what will be used to find the factor of safety against failure. Um, that maximum tilt angle should be less than or equal to 0.4 radians. And the factor of safety against failure should be greater than or equal to 1.5. And for crack section angles of rotation, the sections along the length of the girder should also be checked to ensure that the girder has adequate lateral moment capacity to resist 1.5 times the active moment. It's important to note that the factor of safety, if the factor of safety against failure, Fs prime, is less than the factor of safety against cracking, which is just Fs, the maximum factor of safety occurs right before cracking. Therefore, Fs is equal to Fs prime.